because I have never given any talk in any of the cosmology schools so far. So I hope the talk I will be, the lectures I will be giving are relevant to what you are learning. And I will start with something, okay. Yes, I will start with something very basic, and I will start with giving you the references. These are mainly 4 references. There are many good books on radio astronomy, understanding of radio astronomy. But on the left, there are these 2 books which are considered classic in radio astronomy. On the right, there is a link to which is called Radio Astronomy Blue Book, which is written by people at NCRA, and it is quite relevant to GMRT. And then there are these lecture series which are online at NRA web pages. These were given. These lectures were given during their synthesis imaging workshop. So these are quite useful lectures. You can search for these and look for these references. Now I'll just take a step back and just remind you that astronomy is unlike any other science, because in astronomy, all the events we are trying to look for and trying to understand have happened in the past. That is due to the finite speed of the light. So what we are trying to do is we get some photons, or in case of multi-messenger astronomy, if possible neutrinos or gravitational waves. From these signatures, we are trying to gather these circumstantial evidences and then trying to understand the phenomena which may have happened in our universe. And the assumption is that the physics we understand sitting on Earth, these physics apply to most of the places we are trying to look for the physical phenomena. Now, once you have these restrictions and you can work only with the circumstantial evidences to understand our universe, we can try to gather these information in the best possible way. For example, if you have to get the photons, we can try to build the best of the telescopes, try to get the photons in as many energy ranges as possible, and understand them. But until very recently, like recently in the sense of centuries, until last century, optical astronomy was the main astronomy, which means the wavelengths for which our eyes are sensitive to. And the telescopes were mainly built for optical wavelengths. But there is a problem. The problem is that you can maybe build a very good telescope, and you can try to look at this man on your left. And if you build a better and better telescope, maybe you can see the texture of his clothes, texture of his skin, the scars on his skin or whatever. But you will never have a full comprehensive picture. You will still have only the outer appearance of this human being, unless you take an X-ray of this person and then you get to know the bone structure, and that gives you a better information. So it means that multi-wavelength, if you only have photons to deal with, you may as well gather in as many wavelengths as possible. And this is the basis of astronomy today. It was known in early 20th century and late 19th century itself that electromagnetic radiation is not confined to optical bands. Optical is a very small band of electromagnetic radiation. They are in gamma rays, X-rays, radio. And X-ray and astronomy had already started much before radio astronomy. Other wavebands had started, but radio and was very late to start. And the reason is the following: this table. We thought that as we understand the stars like sun, these are black body stars. So based on their temperatures, they will emit radiation, and owing to the long wavelengths of radio radiation, it was considered that if you look at the black body spectra, if you see on the right hand side, the brightness or the flux or the intensity is so small in radio frequencies that people thought that the sky is very, very dark in radio band. So there is no point looking for astronomical objects in radio band. So that is how the consensus was in the radio band until accidentally Carl Jansky, who is now considered the father of radio astronomy, he accidentally discovered the radio radiation coming from the center of our galaxy. And this was not the experiment he was doing to search for these radiations. These were the accidental discovery which later Groth Reber, he also confirmed, and not just confirmed, he built his own antenna and also created the first survey of our map of our galaxy. And that was the starting of radio astronomy. And this was a very big breakthrough, because if you look at this plot on the y-axis is the atmospheric opacity, and you can see from this plot that it is only the narrowband optical radiation and this broadband radio radiation that these photons are able to reach to our ground, which means we can build the telescope on our Earth itself. We don't have to go to the beyond our atmosphere to do science in other wavelength, like we have to do in gamma rays and X-rays and ultraviolet wave bands. So radio provide us this amazing way to do radio astronomy at the ground level. And as you can see, I am writing the radio wavelength. These are limited by the ionosphere on the lower frequency side, and on the upper side, they're limited by the absorption due to the water vapor. But they are a very broad range. Radio waves are very broad range, unlike optical astronomy. And I must say that radio universe provides a parallel way to understand our universe. On the left is an optical sky, and you can imagine that most of these light is from the stars, and it looks very nice. On the right is a radio sky, and none of these objects are stars. Most of these objects are radio galaxies, far away quasars, supernovae remnants, H2 regions. So none of these, the radio map which you are seeing on the right, none of these have counterparts on the left-hand side. Radio universe or radio wavelengths are showing a very different view of the universe as opposed to the optical astronomy. These are some of the objects I'm showing. On the left side of all of these are the optical images of the same things. In the same scale on the right hand side are the radio images, and I don't have to emphasize this fact that the radio is giving a very different kind of and very complementary information than the optical wavelengths. And currently we understand that when we are trying to study the objects in radio bands, we are often looking at the universe at extremely high energy phenomena of the universe. We are getting an opportunity to look at our universe at very high magnetic field scales, very high velocities, very highly energetic phenomena in our universe, which are not many times not possible to see in other wave bands for that long. In addition, radio universe, most of the radio objects are very far away things, or many of the radio objects are far away things. So it gives us a way to look at our universe in the radio bands. And this is exactly the aim for this particular school is also. And we all know that CMBR is also falls in the radio band. The evidence of the dark matter was also first time seen in the radio maps, rotation curves of the galaxy. So this part I will just very quickly, I think in next 2-3 minutes, I will just rush through and then go to the main parts which I want to convey. So radio emission is mainly two kinds of emission, thermal and non-thermal. In thermal, I think all of us know that black body radiation will produce any object which has some temperature will produce some radiation. And in radio waves, because the radio frequencies are very small, we will be in the Rayleigh-Jeans limit, and the brightness will be roughly proportional to nu square. And these are emission from the optically thick sources. But if you go to the optically thin sources, then there is another emission which will dominate, which is Bremmstrahlung emission. It is also called a free emission. In this emission, you have this ionized plasma, you have these electrons and protons, and electrons in the vicinity of protons, they will produce this Bremmstrahlung emission. And I'm just showing you the formula. I am not getting into the details, but if you want to understand these things more in detail, you can go to some radiation mechanics book and try to understand them. But I'm just trying to give you the variety of the radio emission. This one I am pretty sure you will study, or you may have studied in great detail, because this is very, very relevant to the school you are attending. And these are the line emission, and this line emission is coming from the neutral hydrogen, where this is basically electron flip transition, which in general are prohibited transitions. But since there is so much of hydrogen in our universe, that even though they are prohibited transitions, our universe is filled with these 21 centimeter radiation. And these are extremely important radiation, because this gives us very critical information about our universe, not just the hydrogen content. Since this radiation is at such a fixed frequency, that you can look at these transitions at far away sources, and since you know the frequency, you can find the distance to those objects, and this is how one can understand how far like these objects are in our universe. These images I had shown on earlier on the right hand side, both are showing the neutral hydrogen extent or galaxy, or these are the radio maps in the neutral hydrogen. So the optical is dominated by the stellar light, but radio is dominated by neutral hydrogen. And this is telling us, for example, on the right hand side, that we may think that the galaxy is this small, but actually it is just the starlight which is confined in the smaller area, but neutral hydrogen is gravitationally bound and part of the galaxy to much larger scales. Similarly, on the left hand side, one can see that these galaxies, which we in optical doesn't give us any clue, but in the radio one can see that these galaxies are interacting with gravitationally interacting with each other. So these are bound systems, these are not independent systems. So this information is possible via these neutral H1 transitions. Now there are these non-thermal mechanisms. The most important, in fact, most of the radio sky, we see the continuum emission we see from the sky is coming from the synchrotron emission. The synchrotron emission happens when a charged particle, when it has in the presence of magnetic field, it will accelerate and spiral in the direction, and then it emits synchrotron radiation. And to be able to understand the beauty of this emission is that to be able to do for an electron to emit in the radio band, say for 20 centimeter wavelength, the electron, which has a rest mass energy of 511 kilo electron volt, this electron has to reach to GeV energies. So it means when we are looking at this synchrotron radiation, we are looking at such highly acceleration sites in our universe. And this turns out to be these galaxy jets or supernovae remnants and these kind of radiations. And why these are called non-thermal? One, because they are not thermal. Second, unlike thermal radiation, the brightness increases with frequency. The non-thermal emission, if you see the plot on the bottom right, the right-hand side of the plot, you will see that as you go to higher and higher frequencies, the radiation decreases. And the reason for that is that as you go to if you want to do the radiation emit at higher frequencies, the electrons have to reach to much higher energies, and which becomes increasingly difficult. In fact, at some point you will have a steeper slope as shown in the dashed line. That's because there is a maximum limit has reached and electrons cannot gain energies beyond that, and then they cool rapidly, and that's what decreases the brightness. On the left side, what you see, the increasing part, that is because of the absorption, because synchrotron radiations get absorbed by either the synchrotron self-absorption by the medium itself, which is producing synchrotron, or the external medium, the ionized plasma. The second kind of emission is coherent emission. The coherent emission is where, if you remember your the very basic concept of this emission is that if there is a population of electron, if all of them at a higher energy state, and then all of them makes a transition to a lower energy state, they will emit coherently, and this will have a very high brightness. And we see this coherent emission in many aspects of radio emission. We see maser action happening. Pulsar emission is coherent emission. There are some emitting O and B stars which are emitting coherent radio emission. So there are many many places where universe is showing us the coherent radio emission. So these are all non-thermal mechanisms. And this one, for example, on the left is the optical image which I had shown you, and on the right is the jets coming out of the galaxy, which is emitting in the radio band via synchrotron emission. And that's why it is so exotic in the radio band, but not so exotic in the optical band. One very important concept when one deals with brightness, temperature, or talks about radio astronomy. And what is brightness temperature? So we know that when a system is emitting black body radiation, the brightness is related to its temperature. Black body is connected with, like, temperature is one thing which determines the brightness, and basically it is what is the defining factor of this Planck's radiation law or black body. In radio radiation, for example, in case of non-thermal emission, you can still define a temperature of that system. And in that case, we define a brightness temperature, which has no relevance to the physical temperature of the system. But what it did shows us that if this system was a black body, this must have been the temperature of the system. It is not telling you that the system is black body. For example, if I take a synchrotron emission, from this galaxy signal, say, and if I assume that, suppose what I am getting some kind of brightness from this galaxy, and now I assume that this is coming from the black body radiation, what kind of temperature it will indicate? It turns out to be the temperature is 100 million Kelvin. And it has, in some way, it is not a physical temperature, it is just a brightness temperature, and this is how it is defined. But it does become very important in non-thermal emissions, because if a system has a brightness temperature of 10,000 million Kelvin, or no, 100,000, 10 to the power 12 Kelvin, I'm sorry, 10 to the power 12 Kelvin, then it turns out that this emission should no longer remains an incoherent synchrotron or in a Compton kind of emission. It should be most likely a coherent emission. So this is that non-physical way to determine a non-thermal system. Now let's get to the actually making observations in radio astronomy. And one other thing which everyone encounters in radio astronomy is the signals are very, very weak. For example, if I take a very typical radio interferometric array, which has a collecting area of, or if I take a system, any radio antenna which has a collecting area of 10,000 square meter, and it is pointing towards a radio source which has a flux density of 1 millijansky, which, believe me or not, is considered one of the reasonably bright source in radio astronomy. In 1,000 years of observation, I will receive the total energy of around 10 to the power minus 7 joules, or 1 erg, which is comparable to only a few percent of the kinetic energy of one single falling snowflake. So that is how you can imagine how weak the radio signals are, and that is why the units in radio astronomy are not in terms of CGS or NKS system. We generally talk in terms of Janskys, millijansky, microjansky, and Jansky in MKS system is 1 Jansky is 10 to the power minus 26 watt per meter square per hertz. And 1 Jansky source is considered really bright source in radio astronomy. And and in CGS system, 1 Jansky will be 10 to the power minus 23 ergs per centimeter square per hertz. So this is the unit of Jansky. Oh, actually, I've forgotten. It should be per second also. Sorry. So, and if the source is extended, then we talk in terms of sky brightness, where we also divide by steradian.
Poonam, it's already watt, so it's all right.
Oh, there is, sorry. So yeah. You are right. In ergs, it has to be second, but not in the MKS. You are right. Yeah. So in ergs, I did not say second. So there it should have been ergs per meter square, centimeter square per second per hertz, not here. Right. So then if the source is extended, then we talk in terms of brightness spectrum, and then we also have ox per second per centimeter square per steradian. So this is how the units go in the radio astronomy. Now radio telescopes are designed. Every telescope is basically designed on two basic principles. One is sensitivity of the telescope, means you should be able to observe very faint sources, and the sensitivity depends upon the size of the telescope or the diameter of the telescope, and it is proportional to d square. So which means we want a bigger telescope to be able to collect more light. Okay. The second thing we want is the spatial resolution. We don't want to confuse between two nearby sources in the radio sky. We want to be able to see the sources in best possible way. If there are some structures, we want to resolve those structures and to be able to see those structures. So it means overall one wants a bigger telescope to provide a better resolution and more sensitivity. And since you can see the resolution depends upon lambda over d, and lambda is really high in radio bands, the radio telescopes are generally quite big in size. For example, on the left side, I'm showing you Arecibo telescope, which unfortunately do not exist anymore. It crumbled down last year, or last year. It has a dish of 300. It had a dish of 350, around 350 meter diameter. On the right is the Greenland telescope, which has a dish of around 100 meter telescope, 100 meter diameter. There is one basic difference or two basic difference in the radio telescopes. While all optical telescopes will look similar, because it works in a very narrow range, radio telescopes, because they are 4 orders of magnitude spread in their wavelength, even within the radio band, a millimeter telescope will look very different than meter wavelength or meter long wavelength telescope. And this is why radio telescope have to be designed very carefully, and one has to decide which frequency range one is trying to observe these telescopes. And another one very important difference in between radio and optical telescope is the what is called use of coherent amplifiers in radio astronomy, because in radio astronomy, in radio telescope, there is a preservation of phase information along with the amplitude. So there is a one preserves the phase information is very useful, because there later one can use electronics and do some image synthesis analysis of the data, and then finally get the, without loss of information, recreate the information of the source. This may sound slightly confusing right now, but it will become very, very clear to you when we go to the next lectures, where we deal with all of these things in much more detail. But let's just try to understand in very simplistic terms. So radio waves from distant cosmic source will fall on the antenna, and this will create a fluctuating voltage at the antenna terminus. This voltage which is received by the antenna will vary at the same frequency as the cosmic electromagnetic signal. So this is called radio frequency. Now, in the simplest antenna, I think I have the plot. Yes. In the simplest of the antenna, this frequency, this radio frequency, this voltage will be first amplified by the front end amplifier, because signal is quite weak here, so one needs to amplify the signal, and also one needs to make sure that when you're amplifying the signal of this electromagnetic signal, you introduced as little noise as possible. The moment you introduce an electronics item, you increase the noise of the system. So one has to be very, very careful. So front end amplifiers, or as soon as the radiation is received and you're amplifying these, are made, one tries to make them a very, very low noise amplifiers. After amplification, the signal is passed into a mixer. A mixer is a device which will change the frequency of the input signal, the radio frequency signal. For example, a typical mixer will have two inputs, one for the radio frequency signal whose frequency to be changed, and I'll tell you why we need to change it. And the other is usually it's a pure sine wave generated, and it is called the local oscillator. So now you can imagine that the output of the mixer will be at the beat frequency of the radio frequency and the local oscillator frequency. So which means after the mixing, the signal is now at a different frequency than the radio frequency which was received by the antenna, and this is called the intermediate frequency. Now, the main reason for mixing is that even though most radio telescopes operate at wide range of radio frequencies, the processing required at each of these frequencies is generally more or less similar. So it's very economical to one to introduce this mixer and have separate them out in different intermediate frequencies. And second, also the thing is one uses use of coaxial cables to transport the signal along long distances. Because when we will talk about interferometry, there's antennas are quite far away, and one needs to use these cables to transfer. So the intermediate frequency is usually chosen so that it minimizes the transmission loss in the cable. Okay, so sometimes, yes, so this is what it happens. For example, in GMRT, in the earlier GMRT, radio signals for radio waves were accepted within 50 megahertz to 1.4 gigahertz. And IF intermediate frequencies were at 130 megahertz and 175 megahertz, and also at 70 megahertz. So this is what it is. And now after conversion to intermediate frequency, IF, now signal is again, there is one more amplification. But after that, we take the system to what is called back-end processing. And now it depends upon the science you are interested. If you want to do if you're only interested in getting the flux of the source, you just have a broadband backend. If you want to do a spectral line analysis, you may have you have to put a spectrometer there, and you have to analyze the data. If you want to do the pulsar, you have to put a system which can look for these very, very high time resolution, time domain images of these pulsars. So that I am not going to, but I'm sure Prasun will talk to you about the spectrometers, because those are very important for H121 centimeter analysis. So this is a very basic principle of a radio telescope. And there is one more thing one needs to just remember this thing to deal with the radio astronomy, is that the cosmic source will typically emit radio waves over a wide range of frequencies. But the radio telescope is sensitive to only a narrow band of emission, which is centered around the radio frequency. So within the zeroth order, we can assume the electromagnetic signals falling on the antenna to be monochromatic. So that one has to remember. Second thing is that since most of the sources are and you do know that any monochromatic wave can be decomposed into sum of two orthogonal polarizations, right? That is a well-known fact. Now, since another thing is that most of the sources, or almost all the sources we are interested, are very, very far away from the Earth. And radio telescope is seeing only a very small part of this spherical wave front, which is leaving the source. And so one can approximate this to be a plane wave front. One doesn't need to worry about the third dimension. One can just work in 2 dimensions most of the time. Well, eventually, of course, we will see that these assumptions are no longer true when one wants to do a very, very sensitive imaging in the radio bands. But to understand the very basic concepts of radio astronomy, we will assume that. Okay. And so, for example, if you have electromagnetic wave of frequency nu propagating along the z-axis, the electric field can have like 2 components, one along the x-axis and one along the y-axis. And what I have written these 2 equations, this is one of the most general expression of each of the component of the electric field of a plane monochromatic wave. One can write it this way. And now, these in this formula, AX, AY, uh, delta X, delta Y, all these will, different values of these will give you a different kind of polarization. For example, if you have AY is 0, and then the amplitude will change from minus AX to plus AX. And such wave will be a linearly polarized wave along the x-axis. If your angle is, say, pi by 2 or minus pi by 2, one will get a circularly polarized wave, or in general, you will get elliptically polarized wave, which will have some component of linear polarization, some component of circular polarization. Now I will come to what is called signal to noise in radio astronomy. Now, as we have already talked that in radio frequencies, we generally measure cosmic strength, source strengths in Janskis, millijanskis, microjanskis, those units. Now, what is a signal in radio astronomy? We talk in terms of temperatures. And the signal is also called antenna temperature. For example, we have this antenna. This antenna will absorb power from the radio waves that will fall on it. And this power, if the power of this source is P, then we can measure, we can say that the temperature of the antenna is P over K. And brighter the source will be, the higher the antenna temperature will be. But the life is not that simple. All of this antenna temperature have to be measured against some unwanted elements which are unavoidable, which are also called system temperature. System temperature is simply the power which has, of course, in terms of temperature, the noise which has been contributed to our measurements by emission from various components. For example, it can sky will have some background emission. There will be some even, in fact, if you have, for example, if you have a feed, which we will talk a little bit later, is called a prime focused feed, you may also pick up some signal from the ground which you do not want to pick up those signal. You may also have the receiver noise. All the electronics will produce some kind of noise in the system. For example, sky, as I said, is the background noise. And then you have any lossy element in the feed path can have something, say, called T loss, and then receiver system itself will add the noise to the system. So there are various components which will add to your noise, and the characteristic of this noise is such that if you observe for a longer time, this tau is the time integration time, this delta nu is the frequency in a wider band frequency. It goes as 1 over square root of the bandwidth and the integration time. It means you are going to reduce your overall noise. So it means it is very beneficial in radio astronomy, or in fact, for that matter, in every astronomy, to observe for a longer duration. And also in radio astronomy over a wider band, which of course produces some problems which we will see, and I think Prasoon may take up in more detail, which is called bandwidth smearing and those effects. But so it is, in some way, it is a interplay between the wider band versus avoiding the bandwidth smearing, because that results in loss of coherency in the signal, which again you will probably understand when we go into a little more detail of that, and that will give us a better RMS. So what is something very important in radio astronomy is we call signal to noise ratio. And this is basically, in fact, this equation which I'm showing you, this is the fundamental equation for sensitivity of a radio telescope, of a single dish radio telescope. Okay. And so what we want to do is that we want to have as high value of this parameter, which is called SNR, signal to noise ratio, as possible, to have to have a more confident detection. And why is that? For example, suppose your telescope has a system temperature T says we have a gain G and we have a bandwidth delta nu. Now, what one is doing is we look at the sky, blank part of the sky where we know that there is not source. I'm just giving you the concept, and then we measure the temperature we are receiving in our system. Then we switch to a region where it is containing our source. Now, if the received power increases, right? If your temperature of the antenna increases, it means there is some source in the sky, and we have detected the radio waves from this source. But now imagine that even the blank sky will have some fluctuation, and the temperature of the system will increase. In fact, if you're looking at the galactic center, it will increase quite a bit. But any part of the sky, since your temperature of your system will increase, how are we sure that increase in the antenna temperature is not just any random fluctuation, but it is due to a true astrophysical source? And that is exactly what signal to noise ratio indicates, this SNR. And again, which I had said, I'm repeating again, this S is the flux density of the source. Higher the source is, easier it is to detect it. G is a fixed gain for an antenna. Larger the bandwidth is, easier it is to detect, because the signal to noise is higher. Longer the time duration we are observing it, easier it is to detect it. So in what we generally take is that if this signal to noise ratio is 3 or higher, then we call it a 3 sigma detection, which means we say that we are reasonably confident that what we have detected is a true signal from an astrophysical source. But anything less than 3 sigma is not that believable. So that is what signal to noise is. But let me also just say that this T which I'm writing, or the noise, it is only called thermal noise, which is the noise which is certainly has to be there because of the different system we have, receiver and our electronics is producing. But there are also some extra noise which do get added in our overall noise of the profile of the measurements, and this is called these are because of various other reasons. For example, this noise can increase if we have RFI, radio frequency interference, which can be caused by our cell phones, our television devices, and some satellites, and these kind of things, which I will say a little more when I will be talking about editing the radio data. The RFI is one of the major source of increment in the noise. Another, course, your noise can also increase. Suppose your sources are, your sky is a very busy region. And in that case, you have a lot of confusing sources nearby, and then your overall noise may also increase. And there are also statistical fluctuations which will increase your noise. But signal to noise is a very, I would say, a way to define whether one has detected a signal or not from a source. Now, one of the very important aspect is antenna pattern. Now, so far, we have not been taking into account the shape of antenna or the finite size of the antenna. But it is very important to treat antenna elements more completely. In an ideal way, suppose we will imagine, or let me just come to this a little bit in little bit in detail. It is important to deal with the antenna pattern, because primary antenna and our understanding of the antenna, it'll affect our understanding of the measurements, because it affects the pointing accuracy, the side lobe levels, which will become surely, the noise temperature, the purity of the polarization, if you're interested in polarization observations, aperture efficiency, those things. So what happens, we define primary antenna element to be this piece of equipment, right? This antenna is this dish, which is taking or intercepting this propagating electromagnetic wave from the observed source, and it is making a sample of it available at the input for the first amplifier, if you remember, first front-end amplifier, right? So we cannot just take that our source, for example, our source is just this point source. We have to take into account the how our antenna is behaving, and we will learn very soon that our antennas does not behave what we had seen in the earlier picture. They have these patterns where it is called a main lobe, which is the main primary lobe, primary pattern of the antenna, and then they also have these side lobes. So when we have an image, and which I will show you after we talk about the antenna pattern, that this image are modified as per the antenna pattern, and those effects need to be understand for us to be able to take into account those effects. Okay, so let's just understand in this very simple way that we understand the concept of what is called effective collecting area of the primary antenna, and that I am defining as this a nu theta phi, where nu is the frequency, theta and phi are the direction coordinates. Now, if my antenna is pointed at a source which has a brightness of nu theta phi in units of, and arcs per centimeter per centimeter square per second per hertz per steradian, then the power will not be just simply P. Power received by the antenna will be modulated by this antenna pattern A nu theta phi. And again, we will come to these things also, this also in more detail when I will be talking about the equations of interferometry. We will also deal with these things a little more in detail, but this is how you can imagine if my antenna is working in a bandwidth of delta nu, and from element of delta omega solid angle, the power received can be given by this equation. There is another term I will define, which will be very useful, and that term is A0. If A0 is the response at the center of the main lobe, here, it is the effective area of the antenna, then I also define something which is called normalized antenna reception pattern. Okay, so these are two things, and with this thing, I can also define the beam solid angle of the power pattern will also be modulated by this antenna pattern. So basically, antenna pattern will play a role in every single equation we are dealing with. And one of the fundamental relation of this antenna theory states, in fact, is that this A0, which is the response at the center of the main lobe of the antenna with the pattern A nu theta phi, into this omega beam solid angle power pattern, this multiplication is equal to lambda square, which means what is it telling me? That this omega is in some way a measure of the field of view of the synthesis telescope, right? So for example, if my normalized pattern was just one everywhere, then omega A will have the maximum possible value of say 4 pi, right? And the primary antenna is isotropic and can see the whole sky, but it is not really the case. And another thing you need to know here, since lambda square is fixed for a given observation, given wavelength, A0 into lambda square, this is a fixed constraint, a fixed number. Now, when omega is maximum, A0 is maximum, right? It means the power received is, okay, let me just, I think, rephrase it in this way. I want to have a maximum sensitivity of my telescope. I want a larger A0, right? But if I want a larger effective area of my antenna, my field of view, omega A, which is a measure of field of view, it decreases because it's lambda square over A. It means there is always a trade-off between sensitivity of the telescope versus the size of the field of view of the telescope. For example, if you take two telescopes, for example, Very Large Array and GMRT, GMRT has an antenna diameter of one antenna diameter of 45 meter. VLA has a single antenna diameter of 25 meter. Now lambda over 25 meter versus lambda over 45 meter, so the GMRT will have higher sensitivity, but its field of view will be smaller than the VLA field of view. So there is always this, the collective area will increase, will improve the sensitivity, but field of view will decrease. So this is a trade-off of the antenna pattern. Oh, sorry, trade-off for the of the between the field of view and the sensitivity of the antenna. Now we will. I'm actually quite well aware that this may be quite confusing, but I just want to go ahead and I want to, because I promise all of these things will become much clear to you when we will be dealing with in the next three lectures. So I want to define two more things here. One is the antenna efficiency. For example, the ratio of antenna, ratio of A0 to the physical area of antenna A. It is called aperture efficiency. For example, the physical area of a GMRT antenna is 45 meter, but efficiency is less than 1. So the effective area for collecting the electromagnetic signals is smaller than 45 meter. In fact, at 20 centimeter, the approximate effective area is around 35 meter or so. So that's what is called that defines the antenna efficiency, and it is a very integral part of every single antenna design one will make. The second, the important relationship which tells you that why are we getting these side lobes and these kind of patterns, this comes from this Fourier transform relation. Unfortunately, I'm not going to derive it because it's really going to, because there are other things which I want to cover, and this is I felt one can leave without deriving it. But this is basically, if you have a complex voltage distribution of the field, small FUV, and then if you have in the aperture of an antenna, and then you have complex far field voltage radiation pattern, FLM, where LM are the coordinates in the sky and UV are the coordinates on the ground, and we will talk about this coordinate system much more in detail with images for you to understand. But this is what this is the relation which one can say between FLM, capital FLM, and the small FUV. What that means is, suppose I take a single one dimension and I am taking, this is my FU, this is my antenna aperture which has an aperture edge like this. Based on this relation, this is the radiation pattern I will receive. This is the form of FU on the right top, form of FUV and FLM in the single one direction. So what the Fourier transform relation between an antenna aperture distribution and its radiation pattern, which we'll see in the next lecture, is something which is called Van-Sittert-Jernicke theorem, which tells us about the source brightness distribution and visibility function, and we will introduce all of these concepts. But what is important, it is showing that antenna aperture and its pattern determines how an antenna is going to behave, how it is going to have a primary lobe, how it is going to have side lobes. And in the bottom side, I'm showing you in the two in the more generalized way of showing you this whole plot. So the form of aperture distribution and radiation pressure, radiation pattern are quite connected with each other, and that is a very, very important thing to understand. And as I already said, this is called the main lobe of the antenna, and then you have these side lobes. You have the first side lobe. You have, actually, if you see here, if you can see this tiny thing, You also have a second side lobe, and you also have, what is it called, these points which are called the null points. So there are these various terms which one kind of understands or gets introduced in radio astronomy, and I will be using these terms again and again in next few classes, a few lectures. Yes. So let me just I'm just trying to struggle how to say in a simpler way, and maybe this is the last thing I will cover. So what we do is that when we solve these equations, we see that the antenna nulls will appear at lambda over d, 2 lambda over d, 3 lambda over d. So this is the main primary lobe, this is the first side lobe, this is the second. This is coming at, lambda over d, 2 lambda over d, whereas the maxima comes at half integrals, like 3 by 2 lambda over d, 5 by 2 lambda over d, and so on. And so what happens, for example, okay, this maybe probably will make it clearer to you. Suppose we have a source function and we are measuring it with a beam response, and then this is the power, this is the pattern antenna beam response, and this is the source flux. This will give us this point, and then what we do is that we have a source in the sky and we measure at every point of that source, and we make the image and we recreate the image, right? But in reality, our antenna beam response has a primary and a side lobe. So rather than recreating the sky as it was, we will recreate the sky which will also have incorporated the effects of these side lobes. And no, primary lobe very bright, then first side lobe less bright, second side lobe much less bright, and these patterns. So basically what we will receive, the image we will create in the sky will have a telltale signatures of the antenna pattern, and that is why it is extremely important to understand the antenna pattern. And in the next class, I will tell you, since I have 12, it's 12:55, and I would like to take some questions also. Yeah. Yeah. So in the next class, I will tell you that this kind of image, which is convolved, the source power has been convolved with the antenna pattern. This kind of image in radio astronomy is called a dirty image, and one needs to get rid of the effect of this beam response of the antenna or antenna pattern, and that gives us what is called clean image. So you can imagine intuitively that to get between clean image, or the image we are interested to do our science in, versus the dirty image, the understanding of antenna pattern is very, very important. So I think I will just stop here. I covered slightly less than what I was anticipating, but I'm assuming that I should stop. So I think I'll take any questions at this moment.
Thank you. And now time for question. Please, you can unmute yourself. So please go ahead.
Yeah. And I would just say beforehand that if you have not been introduced to radio astronomy before, these things may sound slightly overwhelming to start with. But I promise that if you had a lot of confusions in the next few lectures, and including after that when Prasoon will deal with advanced courses, I'm sure that these things will start to make more sense to you.
So hi, so am I audible?
Yes, yes.
So yeah, I want to ask something about the bandwidth smearing that you just mentioned. So I could see some tau there. So what is that exactly? So can you explain?
Tau was the time integral time, or how long you're observing your source. There are actually few kinds of times which go into the radio astronomy. One is that how long you're making your observation. Suppose you're making from rise to set, it is just simply how much integration you're doing. There's another time which is called how, for example, what is that minimum time you're doing your observation where you're averaging your signal and getting one single visibility. That assumes that the loss of coherence has not happened when we have collected that signal. But the time which I had shown in that equation was the total time, how much time I have spent on making my observation.
Yeah. Which means that if we increase tau, we will have higher SNR. Yeah, that's clear.
Yes, yeah, yes, you will have higher SNR. Yes, that is true. But there is also a limit. Once you have reached the thermal noise, you cannot improve your noise infinitely, right? So that is also true. Yeah,
Okay. Thank you.
sure.
Good afternoon, ma'am.
Hi.
Ma'am, can you please explain the equation once again, where we had the omega times the A equals to lambda square?
Okay, this, if you actually want to just understand, if you remember your simple diffraction theory, which you just remember that your lambda over d is your resolution element, and if you have a in the very simple terms, if you have a single antenna, this is what your field of view is going to be, or that much area of the sky you are going to see. So here I am just this I was sorry, I'm sorry. So here I was just trying to show you that this omega A, which is the power pattern received at the antenna, taking into account the antenna pattern, and if you have this effective area of the antenna, then what happens is that this okay, I have not given you the proof for this, but if you go to one of the very fundamental books, for example, the book of which is called Cross, he wrote a book in, I think, in 1980s or something around that time. So what happens is that this is a fundamental relationship in antenna theory, which comes out that the multiplication of these two terms, A0 and omega A, is a constant, and which is a lambda square, which is, you can see, is another way of saying is that omega A is indicating the field of view, or it's a measure of field of view of my telescope. So if my antenna A was larger, then my omega is going to be smaller, or I am going to see a smaller view of, or smaller area of the sky. So my main point was that we want larger area, because you remember antenna sensitivity depends upon the diameter square or area of the antenna. But if we want to get higher sensitivity, we are looking at the smaller part of the sky, and this becomes a problem if you want to do a survey of your sky. If you want to look at the wider region of the sky, then it becomes a big problem.
So, ma'am, does the like array antennas solve this problem? I mean, instead of using a single dish.
So we will array antenna is not going to solve this problem. It is going to solve the problem, because suppose you have, instead of one antenna which has a effective area of A0, you have 20 antenna each has effective area of A0. Your field of view is still going to dictated by lambda square over A0, right? But what improves in synthesis element array is the resolution with which you can see, because we will see later that the resolution is no longer dependent upon A0, but it depends upon the largest separation between a pair of such antennas.
Okay, ma'am. Thank you.
Yeah, sure.
Hello, ma'am. I'm not very familiar with the antenna pattern. Can you please repeat how do we get these side lobes?
That is, it's coming, if you solve this equation, if you for example, if I'm taking these two things, for example, this capital F LM, which is the complex far field voltage radiation pattern in the sky, and now if I take FUV, this is what my antenna is seeing, or complex voltage distribution of the field in the aperture of an antenna, and that the antenna which has some some size and some aperture edges, and it is seeing in whether it is parabolic or what kind of dish it is, that pattern, if I take that equation into account, it turns out that these two are related in this way, in some way, can see a Fourier kind of way. And if you take a Fourier transform of this kind of function, you will see that the Fourier transform of this kind of, or how sharply the edges are defined, all of these things, for example, the form of FUV for an antenna, small FUV, is determined by the way in which antenna field illuminates the aperture. Example, suppose FUV is tapered more at the edge of the aperture, there will be a lower aperture efficiency and the side lobes will be broader. So it is just basically solving this equation and trying to get this is just a Fourier transform relation between the two. That is what gives it.
Okay, ma'am. Thank you.
Yeah, sure.
Can I make a quick comment?
Yes.
Yeah. So all of you can go and revise your single slit, double slit diffraction, grating diffraction patterns. So most of these are directly related to those. So if you revise those and then come to these lectures, it will be lot easier to
The circular aperture, the array is circular aperture. They have done it.
Yeah, Prasun is right. Actually, diffraction theory is the heart of the radio astronomy. So if you just revise that, all of these, most of these actually have that at the heart of all of these equations.
So can you please show the first slide where you shown the references?
Yes. So this is, I understand, is a very complicated link, but you just have to search from this name, VLA synthesis engineering workshop lectures and low.
Poonam.
This one is at NCRA webpage. Yeah. Yes.
Poonam, there is a Slack page, so maybe you can just put in these there. So
that's right. That's a good idea. Yes, that's.
I mean, anyway, I can also put. Obviously, I will be using the same references.
Sure. I think other than this the blue book, interferometric and synthesis and radio astronomy, all of three are freely available to anyone and to look at. And in fact, these are much more in detail. These lectures are there because in BLA school, the lectures in radio astronomy are around 20 or more in numbers. So they have certainly done a much more detailed job of explaining every single concept. So one can go into those and understand things a little bit more in detail. And if you really want to go even more basic, then I would suggest there is a book called Kraus, Kraus. That book has a lot of fundamental aspects of radio astronomy, very basic explanations, and one can really try to dig deeper by going to that book and understand. So I will put the link of that also in the Slack channel.
Okay, I don't see any other hands. Please feel free to discuss in the Slack channel if you have any further question.
Sure, yes. I will also be checking Slack frequently. If there are any questions, I'll be happy to answer those.
Okay, that would be great. Yeah. So let us thank the speaker once again, and we'll meet at 2:30. Okay. Thank you.
Thank you. Should I log out now?
Yes.
Yeah. Okay. Thank you very much. I'll see you tomorrow.